Hey everybody, welcome back. In this video, we're going to briefly introduce hypothesis tests for the difference between two means, and then we'll work an example two. So you can see this is very similar to what we have seen before. Our null hypothesis, right, is we're going to always assume that these things are equal to each other, right? So if their difference between them is equal to 0, you do the little bit of algebra, right? You add mu2 to each side, and you just get a simplified, an equivalent null hypothesis that mu1 is equal to mu2, right? So we assume that they are the same. And then the thing we're trying to prove in our alternate hypothesis is, well, if the difference between those two population means is not equal to 0, then that means those two population means are not equal to each other, right? Again, if you just do the algebra, you add mu2 to each side of this inequality, you're left with what's on our right-hand side. So reminder, we saw this in the confidence interval video, but the standard error of the difference between x bar 1 and x bar 2 is equal to the variance from the first sample size divided by the sample size of sample 1. And then you just add the variance from the second sample and divide that by sample size from our second sample. And you take the square root of that whole thing. So our t-test statistic is going to be the difference of our x bars, right? We want to see how far away this difference is from our null hypothesis difference of population means, right? Mu naught 1 and mu naught 2. I guess I can just say the difference, right? The difference between mu1 and mu2 from our null hypothesis, right? But we're always assuming that that difference is equal to 0. So this thing is just 0. This difference minus 0 is just this difference itself, right? So a lot of times we just will write x bar 1 minus x bar 2 up top, and then we divide it by our standard error. And just a note here, we do not need to pool here like we did with our test for the difference between population proportions. Okay, so let's just jump right into an example. So it's going to be very similar, right, to things we've worked previously. We're revisiting our example about the students who have taken piano lessons, right? And their temporal, spatial temporal scores, right, compared to another group. So just as a reminder, population 1 was all preschool children, right, who do take piano lessons. We took a sample of size 34. They took some sort of test measuring their spatial temporal skills, right? So the sample mean of the preschool students that did take piano lessons was 3.6, the standard deviation was 3.05, and the variance was 9.3, all from that first sample, right? So these are sample statistics, sample mean, sample standard deviation, and sample variance. Our second population was preschool students who did not take piano lessons. We took a sample of 44 preschoolers who did not take piano lessons. Those 44 preschoolers got an average score of 0.386 with a standard deviation of 2.4 and a variance of 5.8. So in our last video, we used these numbers to calculate a 95% confidence interval for the difference between these two means. In the first part of that video, we just calculated the degrees of freedom based on the formula a couple of slides ago. So if you haven't watched that video, go back and watch that video to see how we got the degrees of freedom being equal to 61.8 and rounding up to 62. So it wants us to test, use a hypothesis test to prove that piano lessons improve spatial reasoning in preschool children. Test at the 5% level. So the key here is that it improves spatial reasoning. It's not just that these are different from one another, right? Because if they're different, then the group that got the testing, that average could be less than the other average, right? It just isn't the same. So we strictly want to show that the piano lessons improve spatial reasoning, spatial temporal reasoning. So let's start with our HA. So just a reminder, the first population was the group that did have the piano lessons, right? So if piano lessons improve spatial reasoning, then on average, those students' scores who had piano lessons should be greater than the population of students who don't take piano lessons, right? So in our alternate hypothesis, we'll say that mu1 is greater than mu2. And as always, with these differences, oops, I'm so sorry. We're going to assume that they are just equal, okay? That the average score of the students who do take piano lessons is equal to the average score of students who do not take piano lessons. Step 2, we state our alpha, and we're given that here, test at the 5% level. So alpha equals 0.05. Step 3 is where we write out our statistics. So we have X bar 1, we have our sample size 1, we'll have X bar 2, sample size 2, and our degrees of freedom, right, which we have calculated already. We could calculate it here though in step 3 if we didn't have it. So our sample mean is 3.617. Sample size is 34 for our first sample. Sample mean from the second group was 0.386, and our sample size from our second population was 44. Okay. So step 4 has 2 parts, right? So in step A, we're going to calculate our test statistic, which we have right here. X bar 1 minus X bar 2 is 3.617 minus that 0.386. The variance from our first group was 9.33. Divided by our first sample size was 34. We add that to the variance from our second group, divided by the second sample size. And we have to take the square root of this. And we have calculated the standard error in the last video. So I'm going to do it quickly. I should have saved it. So 9.33 divided by 34 is 0.2744. So if you're not sure what I'm doing, go back to that last video and see how we calculated this standard error. So the sum of these two fractions is 0.4078. And then if you take that square root, 0.6385 is what you should get for the standard error. And again, I did this step by step in a previous video. So if you are not getting the same thing, or if you got lost from here to here, feel free to go back to that last video. And the difference between our sample mean 1, sample mean 2 is 3.231. So if we divide that by 0.6385, we get a pretty large number, 5.06. So just to remind everyone, here's our t value, right? 5.06. And we want to go back to step A, right? We see we have a greater than sign. So our nickname for our test when we have a greater than sign in our alternate hypothesis is a right-tailed test. So we want to find the area under the curve to the right of 5.06 on our t distribution with 62 degrees of freedom. So we can do this on our calculator. If we go to second this, we have our t value, right? And we're looking for the area under the curve. So we're going to go down to option 6, which is our t-CDF. That lower value is 5.06, right? And we want everything to the right of it, all the way up to positive infinity. So we do our 1 second comma to get that E. 99 is how your calculator reads or understands positive infinity. So we enter all that into our t-CDF, hit enter again, and we get a very, very small number here. This would be 0 point, and then 5 zeros, 19999. So basically, we'll just say this is less than 0.001. And this, remember, is our p-value. So step 4b was to calculate the p-value, which we just did. It is less than 0.001. Step 5, we compare our p-value to our alpha. So our p-value is less than 0.001. And then we say this is less than or greater than alpha, which equals 0.05. 0.001 is less than, right? Smaller than 0.05, which is our alpha. So in step 6 is our conclusion. So when your p-value is less than your alpha, then you are able to reject the null. Sorry about that. Did not want that to happen. So step 6, because our p-value was less than alpha, right? Step 5, we saw p-value less than alpha. So step 6 is our conclusion. So we can reject the null hypothesis. There is significant evidence to suggest HA, right? Which is that piano lessons improve temporal spatial reasoning. Okay,